Hey everyone. So in this video, I would like to give a brief introduction to RC circuits. That is a circuit that has a resistor and a capacitor in series with each other, and talk about what's happening conceptually in a circuit like that, and then what's happening quantitatively in a circuit like that, and how can we model it mathematically, which ends up being a pretty cool and elegant model, which I'm sure you will agree with at the end of this video. So first, I've got a circuit drawn here. This is what an RC circuit is. You've got a resistor and a capacitor in series with each other. I put a battery there too, and a switch that's open to start. So my switch is right here. I've got open to start. And that's because of the way that I'm going to set up and talk about this problem. So I'm saying that at first, the capacitor starts with no charge on it. So there's no charge stored in the system. And the question that we're trying to answer is what happens to charge in this circuit once we close the switch? So there's a couple of things that we can say for sure, just based on our analysis, our previous analysis of how capacitors work. When we close the switch here and we connect the battery to the circuit, current's going to flow. Current's going to start flowing around this way, being pushed by the battery. And the capacitor will start to fill up, just in the same way that it would if there was no resistor here. Current's going to flow, the capacitor starts to fill up. Eventually, the capacitor fills all the way up. We get the maximum amount of charge, positive charge on this side and negative charge on this side. We get some maximum charge there, and then current stops flowing at that point once the capacitor is storing the maximum amount of charge, because the battery isn't strong enough to push more charge on the capacitor place. So what we expect is that current flows fast at first and then slowly dies off as the capacitor builds up charge. But the resistor adds a wrinkle to this, because what the resistor is doing is slowing the current in the circuit. We saw that when studying resistors, what a resistor does is slows the current in a circuit, and it's serving that same function here. So if we put a resistor in the circuit right here, then what we're doing effectively is we're slowing the flow of charge in the circuit, which lengthens the time it takes the capacitor to get fully charged. If there is no resistor here, the capacitor will charge almost instantaneously. But if we put a big resistor right here, then it might take a long time for the capacitor to charge all the way up. And that's what we would expect any quantitative theory to show, that as we increase the resistance here, we'd expect the time it takes to charge the capacitor to increase. And so that's what we're going for. We're trying to find some quantitative theory that'll return our basic qualitative expectations about what should happen here, but do it with more precision. So let's think about how to model this. So how do we model this? We can use Kirchhoff's loop rules. Two H's in Kirchhoff, which is always weird. Kirchhoff's loop rule. This with Kirchhoff's loop rule. So it's still true. I mean, the analysis that we have to do here is a little bit different than prior analysis we've done. There's no simple way to reduce this circuit in the way that we reduced circuits with capacitance into equivalent capacitance, or circuits with resistance into equivalent resistance. There's no way to do that. But we can still analyze it using Kirchhoff's laws. It's still true that if I take a point here, let's say, and then I take a loop that starts at that point, goes around the loop and ends up back at the same point, it's still true that the change in voltage is 0 around any closed loop here. That's still true, and that's going to be the key to analyzing this circuit. So let's close the switch and think about what happens. So let me close the switch. So I'm closing the switch. So now I've closed the switch. Current begins to flow. So current's going to flow that way, and that current will change over time. We're trying to figure out how the current changes over time. That's our goal here. Equivalently, we can think about how the charge on the capacitor changes with time. If we know that, we could figure out how much charge is being added per time, which would be the current. So let's use Kirchhoff's loop rule. So let's take this green loop that I drew, using this point as the start and end of the loop. So let's use the loop rule. So I pass this battery, so I add V volts in my loop, and then I keep going around the loop. I get to this resistor, and I'm moving with the current as I go across that resistor. So there's high voltage on the left, low voltage on the right, which means it's a voltage drop across the resistor. So minus IR. And then as I keep going, I encounter this capacitor, and then there's a voltage drop across the capacitor, just Q over C. That's the voltage drop across the capacitor. And I'm going from high voltage here, because I'm on the positive side of the capacitor here, to lower voltage on the right side where there's negative charge. So I get a voltage drop of Q over C, and then I'm back to where I started. So all of that has to be equal to 0. In plain language, what that says is the voltage of the battery is spread across the resistor and the capacitor. And you'll notice that that changes over time. At the beginning, when the capacitor has no charge, so when time is small, this term, Q over C, is really small. And basically the resistor dominates and gets all the voltage. So we should expect current to be higher there, because this term is bigger at the beginning. But after a lot of time has passed and the capacitor is maxed out in charge, Q over C is big and the current is small. So for long times, we should expect the Q over C term to dominate here and get most of the voltage. But we're trying to figure out how that changes with time and how the current and charge change with time. So how do we approach this? Well, we can't just solve this algebraically, because I and Q are functions of time. So really this is a differential equation. You'll recall that the current here can be written as dq dt. So the rate of flow of charge in the circuit. And physically what that means here, Q represents the charge on the capacitor. So we're saying that the current is the rate of flow of charge onto the capacitor plates. That's what we're saying. So the rate of change of charge on the capacitor plate is the current in the circuit, which is fine because the current will have a constant value everywhere in the circuit. So we can kind of focus on what's happening with the capacitor in terms of the current, and that'll tell us what's happening with the rest of the circuit. So let me scroll down here because we're going to do some math. So I have these two equations. So if I substitute the second equation into the first, I get a differential equation that looks like this. V minus R dq dt minus Q over C equals 0. This is a linear first order differential equation. And we've seen equations that look like this before, which perhaps we could talk about at some other point. I don't want to go into that here. But we can solve this with separation of variables. So you use separation of variables to solve. And to remind you of what that is, we try to get all the Q parts on one side of the equation and all the T parts on the other side of the equation, and then we simultaneously integrate. So what that looks like is I've got a dq dt. So what I'm going to do is I'm going to move the dq dt part over here. I'm going to multiply everything by C just to make it a little bit cleaner for me later. So that goes VC minus Q equals RC, excuse me, dq dt. So now I want to get all the Q parts on one side and all the T parts on the other side. So I'm going to multiply both sides by dt, treating dq dt as a fraction, which is, you know, if you're skeptical of that, that makes sense. We talked about how this method is justified much earlier this year. And I think I posted a short proof of it, which you could take a look at if you're feeling flabbergasted by treating dq dt as a fraction. So I've got if I do some rearranging here, I can write this as 1 over RC times dt. So I multiplied both sides by dt over RC, and then I divided both sides by VC minus Q. So now I've got something on the right side that just has dq as a function of q, and on the left side, dt is a function of t. There is no t here, so it's just an integral of dt with a constant on it. So now I integrate both sides, and I'm integrating them for equivalent periods. So if I started at time 0, for example, when I close the switch, that's when I close the switch. So this is time when I close the switch. And then I'm going to go to some later time, just some arbitrary time, which I'll call t here, which isn't super careful with my variable labeling, but I think it makes sense. Arbitrary later time. And then on the other side, I'm starting at 0 charge because I said at the beginning there's no charge on the capacitor, which isn't the most general thing we could do, but it makes things a little bit simpler. So this is initial charge on the capacitor, which is the charge at time 0 to be precise. And then we're integrating to some other arbitrary charge at some time. So I'm going to call that Q of t, little q of t, charge on capacitor at time t. Okay, and then the goal is just to integrate both sides, and then we'll get something that we can work with. So let's do that. So let's keep scrolling down a little bit. So if I integrate the left side, I just get 1 over RC times t, evaluated from 0 to t, just gets t. And then on the right side, I get, there's a, from the chain rule, so the 1 over, I could do separation of, I could do U substitution here, and I'd encourage you to work that out if what I write down looks weird to you. But from the chain rule, I get a minus sign that comes out. And then from the larger function, I get a log of what's on the bottom. And then I evaluate this from 0 to Q of t. It's really, I think it's really important to write out the bounds here, because it's really easy to drop the lower bound and think that it goes to 0 when in fact it does not. If you work this out, the upper bound looks like VC minus Q, and the lower bound looks like log of VC. Actually, let me rewrite this again, just thinking about how much space I have. So this is minus log VC minus Q of t plus log of VC. Okay, so I'm going to use log rules to combine terms here. So 1 over RC on the left times t equals minus log VC minus QT over VC. All right, using log rules. And then moving the minus sign over, and also exponentiate. So if I do that on the left side, I've got e to the minus t over RC is equal to VC minus QT over VC. And now the goal is to rearrange this so I get Q as a function of time here. So I'm going to do that. So I'll multiply both sides by VC. So VC e to the minus t over RC is equal to VC minus QT. So then moving QT over and moving terms around, Q of t is equal to VC times 1 minus e to the minus t over RC. This is our result, or a result, one of our results. Okay, what does this mean? This says that the charge on the capacitor as a function of time goes like 1 minus a decaying exponential. What does that look like? if we were to graph this, this this kind of function has an asymptote, because as e to the, so this term e to the minus, wait, let me circle that. This term starts big, or as big as it can get. When time's 0, that term is 1. As time gets bigger, this term gets smaller and smaller. So we're taking 1 minus e to the minus t over rc. So we're taking 1 minus 1 when time is 0. So when time's 0, q is 0. That makes sense. But then as time goes on, we're taking 1 minus something getting close to 0. So when time gets big, qt is just equal to vc. So this kind of function looks like this with a horizontal asymptote. So there's an asymptote here. And that asymptote is, let me move this out of the way a little bit. So that asymptote is just v times c. So what that says is the charge on the capacitor maxes out at v times c. And if you recall at the very beginning, that's what we said we should get. Because when time gets big, current stops flowing. That means there's no voltage drop across the resistor, and the entire voltage drop of the battery is across the capacitor. So we get the charge we would get if there was no resistor in the system and it's just the capacitor. That's the long time scale behavior of the system. Okay, so that's cool. So this is what a charging capacitor looks like. When you charge the capacitor, it goes like 1 minus a decaying exponential. We could also ask what the current looks like. So if we wanted to plot the current here, we could just do, or if we wanted to get a function for the current, we could just do I is equal to dq dt. So if I take a derivative of this, that first term goes away, that constant term goes away. I get vc out front times minus, and then the minus comes down from the exponential. So I get vc over rc times e to the minus t over rc. So I can cancel some stuff here. The c's cancel. So I'll just erase them. So I get I equals v over r times e to the minus t over rc. So I'm running out of space here. But what does this look like? This looks like just a normal decaying exponential that starts at its largest value when time is 0 and decays towards 0. So if I plotted, I'll make a little plot here at the bottom. So if we plot I versus time, we start at some maximum value, and then we just have a decaying exponential that goes down and asymptotes towards 0. The maximum value here for the current is v over r. So right when time starts, let me redraw that r. Right when time starts, current flows as if the resistor is the only component in the circuit. So the current is maximized at v over r, but as the capacitor fills up, it's harder and harder to move charge. So the current value reduces over time. So that makes sense too. So this is a really quick introduction to the circuit analysis you would do with an RC circuit. The last thing I want to mention is we also talked about how if you turn up the resistor, you should expect the time it takes to charge the capacitor to increase. So how do we quantify the time it takes the charge on the capacitor to increase or to fill up? Well, in this expression here, there's minus t over rc. So this whole thing in the exponential is a unitless quantity because we can't have units in an exponential. So that means that rc has units of time. I'll try to write this in a different color. RC, as a quick thing, RC has units of time. And this thing, RC, is called tau, the time constant. And that sets the time scale here. If you think about what turning up RC would do, if I turn up RC in this equation, then this whole term doesn't decay as quickly because it takes longer time to reduce the value here. If RC is really, really short, then this term in general is just bigger and the exponential reduces faster. So turning up RC increases the time of decay of this term, which increases the time it takes to get to the asymptote in this function right here. So RC is a time constant. It characterizes how long it takes the circuit to evolve and for the capacitor to charge in the circuit. And as we suspected, if you turn R up, the time constant goes up. So when you turn the resistance up, when resistor gets bigger, tau gets bigger, which means that when resistance goes up, the time it takes to charge the capacitor, or some characteristic time, increases. But also, this also says that when you turn the capacitance up, it also takes longer for the system to charge, which is maybe a little bit unexpected, but if you think about it, if the capacitor is bigger, you can fit more charge onto it. So naturally it would take longer to charge because you can just fit more total charge onto the plate. So if you turn up the capacitance too, then the time to charge goes up because it just takes longer to put that much charge onto the plate when you're limited by a certain amount of current that can flow. So when resistance goes up and when capacitance goes up, the time it takes to fill up the capacitor increases. Although I should say that when I'm talking about the time to fill up the capacitor, the time to actually fill the capacitor all the way up is infinity. You can never actually get there because it's an asymptote. Like our curve never actually gets to V over C, it just asymptotes there. And so what the RC time is telling you is just some characteristic time that tells you something about the broad behavior of the system. And in the next problem set, we're going to try to drill down exactly on what that means quantitatively. But that's a brief introduction to RC circuits. I hope it was useful to think about them conceptually and also mathematically. And I will see you all soon. Bye.